Hi, Miss Venable here, bringing you a screencastify presentation on electronegativities. So let's review the trend in electronegativities that we've learned about the periodic table. So what we've learned is that as you go down a column in the periodic table, like this alkali metal column, lithium, sodium, potassium, rubidium, cesium, and francium. So go down the column. I'm adding another energy level, and each energy level creates a shielding effect to keep the nucleus's positive charges from attracting outside electrons. And so what happens is actually that smaller atoms at the top are going to have a higher electronegativity because they don't have all of those shells creating a shielding effect, and they're easily able to attract outside electrons. Now, the opposite of this is true if you look across a row. So what happens across a row is that you're filling up the same energy level with more and more and more electrons. And so that means that it's going to have I would say, increased ability to attract outside electrons as it gets more and more electrons in that same energy level. And the way I remember that is actually, I just remember what metals like to do and what non-metals like to do. So remember this, metals like to lose valence electrons, right? They give them away in ionic bonds when they form ions. And non-metals like to gain valence electrons, right? When they form ions, they always take in valence electrons. So they're going to have low electronegativities. They're not going to attract outside electrons. They're actually going to just give up their electrons if they're metals on the left-hand side of the periodic table. And on the right-hand side of the periodic table, they like to gain valence electrons. So they have a greater ability to attract outside electrons, and they're going to have high electronegativities. Now, keep in mind, this trend does not include noble gases. Okay, noble gases in group 18, I've actually marked them out here in red. They have zero electronegativity. They don't want to attract any outside electrons. They are called the noble gases because they already have their stable octet. Their outer energy level is full of electrons and it can't hold any more. And therefore, those atoms don't want to attract any outside electrons at all. So just remember, low electronegativities tend to be down and left, and increased electronegativities tend to be up and right, not including noble gases. So we're going to actually use this electronegativity idea to identify what type of bond is likely if we're given two atoms. So the type of bond can usually, not always, be calculated by finding the difference in electronegativities between the two atoms. And we'll use a table of electronegativities that I'll show you in just a second. And we just subtract. We just subtract and see what the difference is. And it's the difference in electronegativities that determines the characteristic of the bond between the atoms. So it could be ionic, which means they have very different electronegativities, and the nonmetal is going to completely remove electrons away from the metal. We could have a covalent bond, which means that they're going to share the valence electrons. They kind of merge their outer energy level, their cloud of electrons. They merge them. They don't always share them equally. So we have to kind of further differentiate covalent bonds as either being shared very equally, that would be a nonpolar covalent bond, or being shared unequally, meaning the cloud kind of gets shifted more towards one of the atoms, and that would be called a polar covalent bond. So we're going to take a look first at the chart or table of electronegativities. And I've assigned a value. Notice the noble gases here on the right-hand side don't have any value assigned to them because we'll never bond them with anything. All the other atoms on the periodic table have been assigned a value. And this is the electronegativity value or number for that atom. And this is the number you're going to look up for your two atoms that you're trying to bond. And then you'll subtract those two numbers. Now, if the number is 1.7 or greater, if the difference is 1.7 or greater, that means that the bond type will be ionic and the nonmetal will completely remove the valence electrons away from the metal. But if it's less than 1.7, then you get into covalent bonds. And we'll work a little bit later on covalent bonds and molecular structures and determining polarity. We're going to draw what's called Lewis structures. But for now, we'll just learn the classification system. So don't get too caught up in the exact values that you see on the chart and on the type chart here, because different books that I've seen and websites that I've seen have published slightly different values for these. So, I mean, I've seen electronegativity difference of 0.4, this one right here, as being classified nonpolar, completely nonpolar covalent. This chart says it's moderately or slightly polar covalent. So don't get too caught up on, just go with whatever chart your teacher is giving you or with whatever chart is in the book that you're trying to read. They will typically give you some kind of polar bond type chart like this. 1.7 is kind of set in stone. If it's 1.7 or greater, it's pretty much going to be ionic, an ionic bond. Okay, so let's look at a couple of examples. Here is a bond between a magnesium atom. I've drawn it here in the middle. It's got 2 valence electrons. Those are little red dots. And it's going to bond with chlorine. And it has to form 2 bonds with chlorine because each chlorine atom has 7 valence electrons and it only wants 1 more. So it has to have a chlorine over here to give an electron to, and then it has to have another chlorine down here to give an electron to. And we're going to identify the characteristic of that magnesium-chlorine bond. So first, I'm going to look up the electronegativities of magnesium and chlorine, and I do that with my chart. So I go in and look at my chart. Magnesium has an electronegativity of 1.2, and chlorine has an electronegativity of 3.0. So the chlorine is stronger, so it's going to pull the electrons away from the magnesium. But let's see if it's ionic and it completely transfers electron, or if it's covalent and they kind of have to share. So the difference, 3.0 minus 1.2, is 1.8. You just subtract the higher minus the lower value here. So that's going to tell me, since that's a number bigger than 1.7, that tells me that this bond between magnesium and chlorine has got to be ionic. So this would be classified as an ionic compound, which we call salts. Now, you probably could have guessed that, because magnesium is a metal and chlorine is a nonmetal, and typically the bond between metals and nonmetals is going to be an ionic bond, and it's going to make a salt. So that shouldn't have been a surprise for you. Let's look at one that's a little harder to classify, and this one's going to end up being covalent, very slightly covalent in the bond. Overall, the molecule's covalent. The bond is just very slightly polar. And we'll talk more about molecular structure and why it's nonpolar overall. But you have 2 things in this bond. You've got carbon as your central atom, and then you've got these 4 hydrogens attached around the outside. And so we're going to look up the difference between carbon and hydrogen and see if we can classify each of these 4 bonds. So going back to my chart here, carbon is 2.5 and hydrogen is 2.1. So if I subtract those, I get a difference of 0.4. Now, according to my bond type chart here, 0.4 is almost nonpolar covalent, very slightly on the low end of being polar. So that tells me that, yes, which one's pulling stronger? The carbon is pulling on the cloud of electrons a little bit stronger, but not that much stronger. So the cloud of electrons is going to get shifted, pulled away from the hydrogens and in towards the carbon. Now, very slightly polar bond between the carbon and hydrogens. Now, that doesn't mean that the molecule is a polar covalent molecule. Actually, what we find out is, yes, it's covalent, but when we draw the molecular structure later on, we're going to find out that this molecule is actually nonpolar covalent because of the symmetry involved. Alrighty, so that was your lesson on using the electronegativity, table of electronegativities, and the bond type chart to determine what type of bonds you're going to find. Thanks so much for joining me. This is Ms. Venable.